Okay, this video is to show you how to do the first level of the DC single node pair single loop tutorial in Circuit Tutor. So I'm going to click on the button for that tutorial. The first thing you'll need to do generally is to do the introductory tutorial, which is done on the web, and you would simply click this button to do that. And there's actually, in this case, 4 different levels of that tutorial corresponding to the 4 levels of the program. And so it's best to watch that in pieces. One thing I would certainly recommend is that in watching that tutorial that you do take notes, so you'll have those to refer to as you're doing the exercises, just as you would typically do, for example, during lecture or perhaps when you're reading your textbook. Okay, the other thing, and I'm going to skip the tutorial right now, but that's basically multiple choice questions and expository material that explains the concepts to you. Now, the next thing I would recommend you do is to look at examples of the types of problems. So when you click this button, you're going to get problems that are exactly like the ones that you actually have to solve, and it'll show you a fully explained solution about how you do that. And that can be very helpful in understanding what you need to do. One thing I will point out, however, is that the examples can be formatted a little differently than the way you're going to enter equations. So for example, this equation has 2 equal signs. You will not be allowed to enter equations with 2 equal signs. You'll actually do that in 2 separate steps. But for brevity here, it's shown that way. But understand that you cannot enter it that way in the actual exercises. But I'll show you how you do enter it. Okay, now you won't have this thing where you can select the different problem types because that's going to be randomly selected in your case. But I have that, and I have some other buttons that you won't have as well, including some cheat buttons. But let's go through each of the types of problem on the first level and show you how to work them. So I'm going to click the easy button here to start the exercises. So this is one type of problem, and it's asking me to compute a sought voltage here, which appears actually across both a resistor and a voltage source. So the first thing I always need to do, and by the way, you won't have these cheat or skip all buttons, so the first thing you always need to do is to choose the type of circuit analysis. Now this is both a single loop circuit as well as a single node pair circuit because there's 2 nodes. So you could actually choose either method here. And it probably doesn't matter. I'm going to choose single node pair here. And then the next thing you need to do is to determine what type of equation you want to enter. So notice that there are 7 different types, and I'll explain all these different types as we go through the different exercises. I don't want to explain them all at once, but it's better to do that in context. So in this case, because I'm trying to find a voltage, and this is actually very simple because it's just a voltage, essentially of a voltage source, I'm trying to find a sought branch voltage. That means a voltage across a single element, namely in this case the resistor. So I select that type of equation. And now I'm going to be presented with what we call a palette of different terms that you might need to write that equation. You probably won't need all of these. You definitely, in most cases, won't need all of them. But you'll need some of them. And what we're going to do is we're going to drag, or we could also click to bring those terms down. So I certainly need V naught equals something. And in this case, it's not going to be 0, so I have to use this term. And it's basically just going to be a number in this case. So the little number sign indicates that I should enter a number here. If I try to enter something inappropriate, like a letter, it's going to give me an error here and turn it red. So that indicates that you're not entering the type of thing that you need to be entering. So in this case, I can see that the answer is simply going to be 8 volts, but actually though, because the plus side here is connected to the minus side, and the minus side is connected to the plus side, the answer is actually minus 8 volts. So I'm going to put a minus sign here, and an 8 volt there, and that's now proper format, so it turned white, and then I can check the equation. I could have, by the way, also done it this way. I could make that a plus sign and put a minus 8 there. It doesn't really matter, and you can do it whichever way you like. Now I will check the equation by clicking this button, and it'll tell me is it right or wrong. So in this case, I got the ta-da sound, and it got printed on the screen. That means it's correct. And it also gives me a little hint here that I've done one out of one of the necessary equations, and so there's nothing more to do for this simple problem. So I would just click no more equations here. And that tells me I finished the problem. It will also offer me a chance to view a more detailed solution. If I was just guessing, for example, or didn't really understand it, or feel like I'm not very confident with that material, then I can ask for that detailed solution, and it'll give me an expanded explanation. This one's pretty simple, but sometimes they're more detailed than this. And that would be similar to what you get actually when you work an example. So that was the first problem type. Let's do the next one. And in this case, you can see that okay, sorry about the little interruption there. I was confused because the header of this form is actually hidden right now. That's actually an artifact of my screen capture program that I'm using. You won't see that problem, so just don't worry about the fact that you can't see that there. The buttons are all still available. So now I'm going to once again work a problem here. Now this time if I select single node pair, well, I guess it did allow that. If I selected the other type of analysis, which is also possible on this circuit, it's actually going to tell me that that's not really the best way to do this problem in terms of the program. And so it's always best if it tells you that to just use the other method, if both methods are actually possible. So I'm going to switch back to the recommended method, which is this one. Now, in this case, I'm trying to calculate a current, namely a current through a resistor. And so that would be what we call a sought branch current. So that's the type of equation I would need here. So, and once again, this is messed up here just due to my screen capture program. I apologize for that. But basically now I need the I naught equals, this is actually an Ohm's law type of problem. So it's just going to be a voltage divided by a resistance. Or I could actually put in the final answer here just in terms of a number. If I want to do the computation in my head, I could use this term. But I'm just going to do it this way right now. So that's going to be 1 volt divided by 6 ohms. And then I have to very carefully check the polarity here to make sure that I don't need a minus sign. So in this case, the current is going to be flowing indeed counterclockwise from high voltage to low voltage. So in fact, I naught will be positive in this case, so the plus sign is correct. In other cases, it might be negative, and so you have to pay close attention to the sign conventions here, and that's explained in the introductory tutorial in detail. So now I will check the equation, and it is correct. And again, that's all I need to do here, so I say no more equations. And in this case, however, I didn't give a final answer. So one of the things to point out is that Circuit Tutor, like many programs, does not accept fractions as answers. You have to give it decimals always. So in this case, it just wants a decimal number here, so that would be 0.167. Sorry, 167. And then I can check that number. And again, the border is missing on my form, but that's just an artifact here. Okay, so that's done, and now there's the correct solution. I'm going to do the third problem type. And in this case, I'm looking for a voltage. This is again an Ohm's law type of problem. And I'm just going to choose a single loop in this case. Again, I could do either, but this is probably the easier method here. And now, since I want a voltage, again, I need a sought branch voltage equation. And now I have a different palette of terms because this is a different situation. So it'll always give you the appropriate types of terms to pick from. So I'm going to need V naught equals, in this case, I'm just going to, actually let me just do this one in my head. So I'll put in the final number here. I can see 1 times 6 is just going to be 6 volts using Ohm's law. Okay, and again, I check that that should be a plus or minus sign in this case because the current's flowing into the plus sign. That's a passive sign convention. So I do need a plus sign here. So I'm going to check the equation. Now let's suppose I put in a minus sign just to show you what happens. So I know that's wrong. So it's going to tell me that's not correct. And in fact, on these very simple problems, you only get, basically, you can't make any mistakes or you lose credit for the problem. However, you can still finish the problem if you want, or you can just give up and start a new problem. Either way, there's never any penalty in Circuit Tutor for making a mistake like this. You just have to work another problem of the same type. So in this case, I can either give up or I can just finish working the problem. So I'll just finish it here and just change that to a plus sign. And notice it says here, credit no longer available for this problem. When I check it, and it again reminds me of that, and now I'm done. And it says I completed it, but I won't get credit. So, and I can still view the detailed explanation, or I can go view examples if I'd like to do that. And so this explains about Ohm's law and the sign convention briefly. But I would have to go back and do another version of that particular problem to get full credit. So I'm just going to skip that for now and go on to the next one. So once again here, this is now trying to find a current, but now there's a current source. I'm going to use a single loop analysis here. And in this case, I need a sought current, because that's what I'm asked to calculate. And so I'll just say I naught equals, in this case, I really have very few choices, so it's not going to be 0, so I have to use this term. And by the way, I can always clear the equation if I need to start over for some reason. I don't need that here, but you just do that and we can recreate it. If you put the wrong type of term in there and you decided that's supposed to be a 0, then you can just drag a term out of that area, and you can edit anything you've put in here. So in this case, I want this. So now this is just determined by the current source. So notice that this is the 5 amp source is going to make the current flow clockwise, whereas I naught is in a counterclockwise direction. So that's opposite senses. So here I need a -5 rather than a +5. And by the way, if at any point I'm confused about the interface, I can also click the help button here. And that will give you some written help to complement this video help. And that gives you some extra information. There will also be a video help button. It's not showing up yet here because I haven't finished recording the video, but eventually there will be a video button here as well. If you want to view this video help at any point, you can do that right in the middle of a problem. It won't stop the problem or cause you to lose credit for it, so you can always view the help in the middle of problems. Okay, and you can also give up on a problem at any point just by clicking this give up button. It'll ask you if you're sure. If you do give up, again, there's no penalty. You obviously won't get credit for this problem, but it will show you the fully worked solution to that problem, and it'll allow you to work another problem of the same type. Okay, so I'm just going to give up on that one and then go on to the next one. And now this one is a little bit different because it's asking me to find a dissipated power in the 9 ohm resistor. Now that's indicated by the gray label on the element. That's sort of our code for dissipated power, as it explains here. So now I'm going to do a single node pair analysis here, which determines basically what type of terms I have available. And now I have to select sought branch power because I'm trying to calculate a power rather than a current or a voltage. So that's one of the other types of equations that you may need. And notice this has quite a few more terms available, so I have to pick the appropriate one. So I certainly need the dissipated power 9 ohm resistor equals something. And in this case, because I've got a voltage source across that, the easiest equation to use is probably V squared over R, as you learned in the introductory tutorial. And since it's a definite value of the voltage, I'm going to use this value. So the little alpha here, by the way, in this term, that indicates that you would be putting in a letter rather than a number. And this is the crosshatch there, of course, is a number symbol. And if I hover over that, notice down here at the bottom of the form, it tells me what that term is actually good for. It's for a power dissipated in a resistor in terms of a sought or control voltage. Well, I don't have a sought or control voltage here, so that obviously wouldn't be the right term to use. Okay, so now I just, again, fill in the blanks. This is going to be 5 volts divided by 9 ohms. And for power, dissipated power is always positive in a resistor, so I would never need a negative sign here. And I can just check that. Indeed, that's correct. And since that's all the equations I need to enter, I just say no more equations. And then, once again, I need to evaluate that. Now, if I'd used the watt term there, I wouldn't have to evaluate it now. I would have done it before. It would have been 25/9, whatever that is. And now I just evaluate it with my calculator. Since I didn't do it before, it's going to be 2.78. Check that, and that's the correct answer. Okay, so I finished that problem. And again, it will give you detailed explanation if you want to see that here. Okay, the next problem type is again a power problem, but this time I have a current source rather than a voltage source. So I'm going to use a single loop analysis in this case. And again, I want a sought branch power. And now it's giving me, notice, different terms because it's a different type of problem. So it'll always give you the types of terms that are appropriate to the problem that you're working. I'm sorry, I take that back. It's actually the same set of terms, but in some cases it may be different. Okay, so in this case, I want to express this in terms of the fixed current of the current source, since that's the easiest thing to do. I could use, for example, this value if I want to compute what V would be using Ohm's law. So it's possible to use this term. It's possible to use this term as well. I'm just going to use this one, I think, this time. And so that'll be 9 amps and 3 ohms. And again, it's always positive for a dissipated power. So I check that. And then I'm done. And now I can see that I have to evaluate that numerically. So that's just going to be 81 times 3, which will be 243 with my calculator. And you do need a calculator, of course, for all these problems. I'll just check that. And that's correct. So I'm done with that problem. And again, you can view the detailed explanation if you like. You don't have to, but that might be helpful. I'll do the 7th type of problem now. And again, this is asking for power, but now this is a little different because it's the power of a source. And that's a little bit trickier to find. In this case, it would be the power dissipated in the resistor, but it's not going to let you enter it that way because it wants you to learn how to do this in more complicated circuits where that wouldn't necessarily be possible. So I'm going to do a single node pair analysis here. And now again, I need a SOT branch power. And also, it's pointing out now that I actually have 2 sets of terms that I can use for power. And in fact, I may need that second set. So they're available via these radio buttons here that are being highlighted. So if you can't find the term you need, this is where it is. Okay, and it's telling you that right here. So it helps to read these little pop-ups. They'll help you understand the interface. Notice also that in this case, it's done something it didn't do before, which is that it actually assigned a reference node with a little ground symbol, and it labeled the voltage of the other node as V1, and it's color-coded those nodes for you. And that means we're going to have to use a little bit different approach here. So now we have the power supplied by the 6-volt source is equal to something. I could just enter, if I want to compute it some other way and just put in the number, I can certainly do that. It will be, in fact, V squared over R, so it'll be 36 watts. I could just enter that value, but I'm going to show you a different way using the other terms. So these terms are a little more complicated because they involve parentheses. So in this case, I need something with a left parenthesis. So it's going to be one of these 3 terms. In this case, because I know the voltage, that would be the appropriate term to use. These other things are actually for dependent sources, and there are no dependent sources in this problem, so that wouldn't be appropriate here. So I'm going to use that, and then I need to put a term in the middle. So this is going to be the voltage, and remember it's V times I. So basically, it's going to be the voltage multiplied by the current from that, and I can find that, for example, using Ohm's law. It'd be one way of doing it in terms of the node voltage. Now, I always need to, of course, close my parentheses, so I put a right parenthesis in there. If you don't have closed parentheses, the equation will not be valid. It won't be accepted. So it's just like doing algebra. You have to have fully closed parentheses when you do this. So now I'm going to enter the value as 6 volts, and then this current flowing in this direction out of that source is going to be basically V1 divided by 1 ohm. And that is not correct. Okay, so unfortunately I made too many mistakes here, and so I'm not going to get credit. And the problem there was that the current flowing out is actually negative V1 over 1. That's because this is the supplied power. So now, if I change the minus sign there, that would actually be correct. And you may say, well, why do you have a negative number there for a power supplied by a source? The answer is that V1 is itself negative. That's the trick here. So now I need to enter a different type, and it's actually giving you a hint here. It's saying that I still need to do a voltage constraint equation. So what is that? Well, it's basically, I just selected off the menu, voltage constraint, as it's telling me to do here, basically. And that means that this voltage source is constraining the value of V1 to actually be negative 6 volts, because the plus side is at ground and the negative side is V1. So I need to write an equation there that says V1 equals negative 6 volts. Now the N stands for an integer. In this type of problem, it's always going to be 1. In more complex problems you do later in the course, then it can have different values. But right now it's always going to be 1. And as I said, this has to be a negative 6 volts, so it's going to be minus, and this will be a 6. And if I check that, that's going to be correct. So now I've written all the equations that I need. In this case, I needed 2 equations. And now it's going to ask me to basically substitute this value into here to compute the answer, which I can see is going to be 36 watts. So of course the power supplied by that source, as you'd expect, is positive here. So I check that value, and it is correct. And again, I'm done, and I may want the detailed explanation here, which is provided here. and it explains those sign convention issues that I just talked about. Okay, I didn't get credit, however, because I made that mistake. But it means I just work another problem of the same type, and I will get the credit if I do it correctly the second time. So that's just where the learning experience is. Okay, the last type of problem here is involving power supplied by a current source. So I'm going to do a single loop analysis here. That's usually better when you have current sources. And in this case, again, I need a SOC power. And it's going to tell me about these different palettes here. So, oh, and that beeped because that was still flashing. You have to wait till it's done flashing before it'll let you do anything else. So that power is equal to something. And I could just enter the value here. If I say, well, I know that power is going to be 1 amp quantity squared times 6. It's going to be 6 watts. So that is a way to bypass using the parentheses terms. If you want to use the parentheses terms, you'd come over here. And again, in this case, they're a little bit different because you have a current source. So I'll just do it this way, I guess. I'll do that. In this case, that's going to be the current. And then you have to multiply it times the voltage, which again would be the voltage developed across this resistor is also going to be across the current source in this case. So you could use that term, for example. Or you could just compute the value of the voltage and put it in this term. That would be another way of doing it. In fact, let's just show that as an example. And then close parentheses. And so now I'm going to have 1 amp, and then this is going to be 1 times 6, or 6 volts. And that will be the correct answer. And since I didn't use the mesh current here, it doesn't require me to write a current constraint equation. Had I used the other term, I would have then had to write a current constraint equation, but I didn't have to do that here because of the term that I chose. Okay, so I just put the numerical computation, very simple there, and check that. Okay, and that's done. And again, I can always look at the detailed explanation. And now I'm basically done with this level. Well, I would be had I not made those mistakes that I made on purpose. But when you are done, by the way, you can always continue to do additional problems. If you feel like you're still not confident with the material and you want to do some extra problems, you can always do that even if you finish all the required problems on the level. It'll say completed, but it doesn't mean you can't go back and do look at examples and or work additional problems. And if you're not feeling confident with the material, that's probably a good idea to make sure that you'll be able to do well on the exam problems. Okay, that's it for this particular level. Thank you.